So yeah, I'm going to say to emphasize again, please make sure to stick to the 30 minutes rule by any, chance. I mean, don't go above that because we have now four talks today, and so we have to be very strict about the time frame. Of course, your material is in your slides and your paper,
Mhm.
so still
Mhm.
it will show itself when I read it later on. So 30 minutes is the rule. And
Awesome.
we will have three speakers first, and then we will have a break for 30 minutes. Alex will join at 4 because he has to come from school to home to give this talk. Um, yeah, okay. So, yeah, Baljeet, yeah, please go ahead. Your turn.
Okay. Thank you everyone for attending. Today I'm just gonna give a rather simple talk on the correspondence between two-dimensional TQFTs and Frobenius algebras. So TQFTs, as all of you might know, has its origins in physics, where we study the evolution of the space of states only due to the non-trivial topology of space-time. So we don't consider any like the Hamiltonian tildes the wave function. This is an axiomatic theory like quantum mechanics, and the axioms were laid down by Atiyah based on some of Witten's work in this paper by 1988. It was
Sorry,
also,
sorry. Is there a blank screen?
uh, can you see the 2 points? Hello?
I can see quite fine.
I'm seeing it fine as well. Yeah.
Okay,
Okay.
sorry. I see it now.
Okay.
Yeah.
Yeah.
Oh, okay. Uh, yeah. Can I continue?
Yeah. Yeah.
Yeah.
Go ahead.
Okay. So these axioms were inspired by Siegel's axioms of conformal field theory. Mathematically, this is also quite interesting because TQFTs in certain dimensions can help in calculating invariance of manifolds. In 3 dimensions, for example, they are related to knot invariance and Jones polynomials. In fact, actually, they have become more of a mathematical than physical phenomena, and which is nice because today we are not going to be looking at the physics side as much. We are mostly going to be focused on the mathematics. There are other physical motivations as well. Some topological phenomena in 2 dimensions. Quantum gravity is supposed to be a topological quantum field theory. John Simmons theory, which we have seen a couple of presentations on, is also a TQFT. And there's in condensed matter physics, there's this topological phenomena that occurs quite often, which is called the fractional quantum Hall effect. I think it's there's also something called the integer quantum Hall effect, but yeah. So we have a lot of motivations to study this relationship between topology and physics. So before we get into it, though, before we get into the axioms, let's just look at some preliminaries. First of all, we have we have cobordisms. So suppose we have two manifolds which are closed. An unoriented cobordism is a manifold one-dimensional higher such that its boundary is just the disjoint union of the two manifolds. I have some examples. Now, all three of these are cobordisms between two circles. You can see that the middle one is different in the sense that it has a genus 1, but the other two on the corner, the left and the right side ones, seem equivalent. And in the unoriented case, they are. It will be obvious shortly why I have represented the same thing in two different ways, though. So if we have an oriented connected manifold with boundary, we can classify its boundary into one of two types, depending on its orientation. It's the in boundary or the out boundary. Now, there is a rigorous way of defining what an in boundary is and out boundary are. If you're familiar with how charts around boundary are defined, there's something called as half space charts. Using that, we can define a normal, and depending on its orientation, where the normal is pointing, will tell us whether or not it's an in boundary or if it's an out boundary. However, for our purposes, and since we are mostly focused on two-dimensional objects, an intuitive description will be more than enough. So now what we can do is define a notion of an oriented cobordism, where if we have sigma naught and sigma 1, S to n minus one dimensional manifold, an oriented cobordism between them is a cobordism such that sigma naught is the in boundary, whereas sigma 1 is the out boundary. Now it will be clear why, as in an oriented case, these two cobordisms are different, where in one case we have a cobordism from a union of two circles to the empty set, and in the other case we have just a cobordism between two circles, from one circle to another, that is. We will maintain this convention of displaying all the in boundaries on the left and the out boundaries on the right. We also mentioned like briefly what that these two cobordisms in an unoriented case were equivalent. So formally, an equivalence between two cobordism is just a diffeomorphism. So if we have two manifolds sigma naught and sigma 1, and we have two cobordisms between them, they are equivalent if they are diffeomorphic as manifolds. We can use this to define our category n cobord as a category with objects as n minus one dimensional manifolds, and morphisms as our cobordisms up to equivalence, that is, up to diffeomorphisms. Another thing that we're going to come across in this presentation are coalgebras. Now, coalgebras are category theoretic duals of algebras, category theoretic in the sense of reversing arrows. I'll demonstrate shortly. So we know that algebras are just vector spaces equipped with a multiplication map. Similarly, a coalgebra is just a vector space equipped with a co-multiplication map. These often go by different name: coproduct, deconcatenation map, etc., etc. But anyways, it's just a similar map, just that the arrows are reversed. So now, of course, we need to define some properties of co-multiplication, which are dual to multiplication. So to start, we know that an algebra is said to be associative if the first diagram that I've displayed here, the one on the left, is commutative, that this diagram is satisfied. And it is said to be commutative if the second diagram is commutative. Here, the tau is just a torsion map which just sends A tensor B to B tensor A, so it just reverses the order. You can see how these diagrams just correspond to associativity and commutativity. Why I have written them in such a confusing way is that, not confusing, but in an involved manner, is that now we can use them to define dual notions of co-associativity and co-commutativity, where we replace our multiplication by co-multiplication and just the direction of arrows. So, and a coalgebra is said to be co-associative if the first diagram is commutative, and it's said to be co-commutative if the second diagram is commutative. Similarly, we have the property of an algebra being unital, and we describe that if it has a unit map, just given from K, where K is the field over which we define this algebra to be. Similarly, a coalgebra and this unital map needs to satisfy a commutative diagram, which I have written on the left. Similarly, a coalgebra is said to be co-unital if it has a co-unit map, just a dual version of the same map. And it too needs to satisfy a commutative diagram. So basically, co-associativity, co-commutativity, and co-unital all just need certain commutative diagrams defined by needs to be satisfied, and that need to be satisfied. So that's all we need to know about coalgebras for now. So let's begin by describing our axioms of topological quantum field theory, which were given by Atiyah. So in D plus one dimensions, TQFT gives us two things. One is, for every D-dimensional manifold, we get a vector space. This is supposed to be our space of states, the one that we see the evolution of. This can also be required to be a Hilbert space. In some cases, we do put that additional condition. And for every D plus one dimensional manifold with boundary, its boundary being a D-dimensional manifold will be a vector space. This D plus one dimensional manifold will be an element in that very same vector space. So these are the two objects that a D plus one dimensional TQFT will give us. Now these two objects are subject to some axioms. First is that this map Z, which associates to these manifolds to vector spaces and their elements, is functorial with respect to orientation-preserving diffeomorphisms. Thus, a diffeomorphism between, or like a smooth map between manifolds, will give us a linear transformation of vector spaces, and a diffeomorphism between them will give us an isomorphism of vector spaces, so on and so forth. It is involutive. So suppose we have a d-dimensional manifold with the opposite orientation, then it will be associated to the dual of the original vector space. And finally, we have the multiplicative axiom, which says that disjoint unions just correspond to tensor products of the associated vector spaces. It also implies that to the empty space, we just associate the base field lambda. Another thing that I would like to note is that in the original paper, Atiyah refers to this as a d-dimensional quantum field theory, not a d+1. But in some other papers that I referred to, there was some inconsistency between what to call it. I'm sticking with d+1 for now, but I don't think it matters. Just consistency is all. Now, what does...
Baljit, I mean...
Yes, sir.
Yeah, this condition you have Z of M belonging to Z of boundary of M.
Mm-hmm.
I mean, Z is your functor, right?
Yeah.
So it takes values in finite dimensional vector spaces, right?
Yeah.
And now, when you write this, what does this mean? This finite dimensional vector space belongs to another vector space. You mean it's a subspace, or what is it?
No. Z of M is not, Z does not take the Z. If we take a d+1 dimensional manifold, it will give us an element in the vector space represented by the vector space of delta M, represented by delta M. So its boundary will correspond to a vector space. The manifold corresponds to an element in that very same vector space.
Yeah. Okay. So, but it's a bit. Yeah. Okay. We'll talk about it later. That's okay. Yeah. Good.
Okay.
Yeah.
Okay. So
Sure. No problem.
Here is where we get to the original main thing, is that now that if we have an oriented cobordism from say sigma naught to sigma 1, we basically have a cobordism here, sigma naught and sigma 1, since one is the in boundary, one is the out boundary, they have opposite orientations. So Z of M is in this vector space, which is isomorphic to the space of homomorphisms between the two vector spaces. So basically what we can do is we can see an oriented cobordism representing a linear transformation from the vector space given by sigma naught to the vector space given by sigma 1. So what we have is that a TQFT is just a monoidal, is a functor. We say monoidal because of this is a property of the categories that we define. Is a functor from the category N cobord that we just defined to the category of vector spaces over the field K. Moreover, we can also define the category of TQFTs over a field K as a category with objects being these n-dimensional TQFTs, and morphisms being natural transformations of this functor. Now, however, since today we are just going to be focusing on two-dimensional TQFTs, let's focus on describing the category of two cobord. So since the objects need to be closed-oriented manifolds, these are just oriented topological circles. So basically what we have is just disjoint unions of circles. What we do is to every natural number n, we just assign an element of this, which is just given by the disjoint union of n circles. And these are our objects. Morphisms, again, are oriented surfaces with boundary. And so a morphism from n circles to m circles is just a oriented cobordisms, is an oriented cobordism. However, we do understand the topology of surfaces. So what we can do is we can actually break down and we can actually understand two-dimensional cobordism quite simply. So what we can do is we can say that every two-dimensional cobordism can be generated by gluing copies of these 5 basis elements of these. Now, now I'm just gonna give a small sketch of the proof of how we can do that. What we can do is we start with one cobordism and we can break it down into its disjoint unions using this element called the twist. All that this twist does is it reverses the order of our circles. It does not, and I know it might seem from the diagram that these are self-intersecting, but they are not. None of them goes over each other. They are just two cylinders which reverse the order of the circles. Sometimes this twist element is also listed as a generator, but sometimes it's not. So how this works is, suppose, consider the first image here, where we have a 1-to-1 cobordism, that is just a cylinder, stuck in between a 3-to-1 cobordism, this connected component. What we can do is we can attach a twist element on the left and the right side and separate it, as you can see in the last image, separate the 1-to-1 cobordism out. Thus, we can write every cobordism as a disjoint union of connected components. So improving the statement for a connected component might suffice. Moreover, we have the theorem of classification of surfaces. That is, a closed-oriented surface can be uniquely determined by its genus. We, however, have a manifold with boundary. So if we give the number of its in-boundaries, the number of its out-boundaries, and its genus, we should be able to uniquely determine a cobordism up to its equivalents, that is, up to diffeomorphisms. Specifically, we can say that a two-dimensional cobordism will be diffeomorphic to its normal form. What is a normal form? Let's just take an example. So suppose we have a cobordism from 5 circles to 4 circles, and it has a genus of 4. This is what we define as the normal form of this cobordism. And what we claim is, because of the theorem on classification of surfaces, this will be every 5 to 4 cobordism with genus 4 will be diffeomorphic to this space. And every such normal form can be constructed using our 5 basic components. Thus, we have proved our result. And this is all we need to know about the category of two-dimensional cobordisms. Next, we move to the second part of our presentation where we describe Frobenius algebras. So here, to start with, we consider just an associative commutative algebra with a unit over a field K, and we have this multiplication map. In this case, we have the following lemma, that 3 statements are equivalent. First is that we have that the algebra is isomorphic to its dual. Second is we have a linear form which does not contain any non-trivial ideals. So any element any ideal contained in this has to be trivial. And finally, we have a pairing, a non-degenerate associative 2 form. Now, if any of these conditions are satisfied, we call A a Frobenius algebra. Conventionally, we pair it with the defined linear form F. We call it as its Frobenius form. So now that if we have a Frobenius algebra with multiplication map beta, we can see that the dual of this map associates to A star, that is the dual of A, a co-associative and co-commutative coalgebra structure. However, note that in the previous slide, we see that for a Frobenius algebra, we have that it is isomorphic to its dual. So what we can do is we can construct an isomorphism between A star tensor A star and A tensor A. What this does basically is it defines a coalgebra structure on A. Thus, we have that a Frobenius algebra is an associative, commutative, and unital algebra, and also a co-associative, co-commutative, co-unital coalgebra. However, can we go the other way around? Given a space which has both an algebra and a coalgebra structure, can we say that it is a Frobenius algebra? Almost. Long story short, just one commutative diagram needs to be satisfied, given by this. This just says that the co-multiplication map is a map of modules. That is, we consider A as an A module. This just shows that co-multiplication and multiplication are compatible with each other. There is a lot more that can be said about Frobenius algebras and describing them, and even the category that we're going to describe. More or less, we're going to stop here after this final definition. Is that that final definition is the notion of a map of Frobenius algebras. It is just a morphism which pulls back the linear form. If, moreover, this morphism is also an isomorphism of coalgebras, then we just call it a Frobenius algebra isomorphism. Why we need to define this is just to define the category of Frobenius algebras over the field K, where morphisms are FA isomorphisms. So we are going to stop the Frobenius algebra section over here, but there is quite a bit more to be said about them. So now that we finally understand both the category 2 cobord and Frobenius algebras, let's see how they are equivalent. TQFT is over 2 dimensions. So each TQFT over 2 dimensions induces a Frobenius algebra structure on Z of 1. Here, note that 1 represents just the element, which is one circle. So the vector space given by that will have a Frobenius algebra structure over there. Here we define we have to define a form, which is going to end up being the Frobenius algebra form, and that is going to be one of the elements, one of the 5 basic components that we defined earlier. I'll show in a second which element it exactly is, but after defining that, we can construct basically all of the other components as well. So here you can see, I'm sorry. Here you can see, I hope my cursor is visible, that this element called the depth of a circle is associated to its one form. The other dual, the birth of a circle, is associated to what we're going to have the unit, co-unit element, the unit element. We have the pair of pans associated to the multiplication and the co-pair of pans associated to co-multiplication. Note that since topologically cylinders are trivial, we say that cylinder induces an identity map. However, just this definition does not suffice. We also need a lot of commutative maps which need to be satisfied. The commutative maps which need to be satisfied by beta for associativity and commutativity, by alpha for co-associativity, co-commutativity, and for F and G for being unital and co-unital. These maps, these equivalences, are going to be given by topological equivalences. So we have the classification of surfaces, which says that if given number of n boundaries, m boundaries, and genus, we have that the two spaces are equal. So we have the following 2 cobordisms will be equal. In the first case, we have an equivalence which gives us the associativity of beta. And in the second case, we have an equivalence which gives us the co-associativity of alpha. Here we can see that this equivalence basically just corresponds to one branch of this commutative diagram. Each side of each equivalence corresponds to one branch of a commutative diagram. So overall, these correspond to the following diagrams which given below, being commutative. Similarly, we have these equivalences. The first one here just shows how adding a cylinder is just a trivial action. So as the cylinder behaves as the identity, and the second equivalence just shows how F and G behave as the unit and the co-unit respectively. Actually, I think I just messed up the labeling here. F should be G and G should be F. And finally, note that we define the twist map, which reverses the order. So in the Frobenius, when we descend to an algebra case, it acts as the torsion map. So these equivalences give us the the commutativity of the multiplication and the co-commutativity of the co-multiplication. Thus, what we have yet now defined is an algebra and a coalgebra structure on A. As we saw earlier in a theorem, all we need to now see is the commutativity of this diagram, which shows that the co-multiplication and multiplication are compatible with each other, and that is given by this topological equivalence. Again, we can see that each side here in this case is just corresponds to taking beta and then alpha, and this corresponds to taking first alpha and then beta. So this topological equivalence gives us this, and what it ends up proving is that A, F is in fact a Frobenius algebra. Now the nice thing about this proof is we can also work backwards. So given a Frobenius algebra, we can define a topological quantum field theory which associates to every union of n circles, the space A tensored with itself n times, and the same mapping of the base components with the algebraic structures. So what we have defined here is an equivalence of categories, of TQFTs over the field of K and Frobenius algebras over the field K. Now I'm mostly done, and I am also almost up on time. So just before leaving, let's just look at a few two examples of Frobenius algebras and their corresponding TQFTs. First, we have group algebras corresponding to a finite abelian group. These are just finite sums where the elements of the algebra K, the field K are components, are our coefficients. We can define the Frobenius form. And now for a cobordism from M to N with genus 0, that is going to be defined by which specific group and field we are choosing. But if we are given a cobordism with a higher genus, we can just define it in terms of the one as genus 0. We just have to add a factor of order of h raised to g. And finally, we have the space of truncated polynomials, where every polynomial of degree higher than equal to a fixed n is trivial. So we quotient out the ideal generated by x to the n. Here we take the element, which is the monomial of the highest non-trivial degree, and we dualize it. That is our Frobenius form. This TQFT sends every cobordism with a genus greater than 1 to the trivial, the 0 map. So these are a few Frobenius algebras. There are a lot of other Frobenius algebras. So there's something called as the de Graaf-Witten model, which I'm going to be honest, I tried understanding, but no. And I mentioned earlier that two-dimensional quantum gravity is also a TQFT. So there are Frobenius algebras associated with that, and they come up in a lot of other spaces. But for now, this is going to be my presentation. One thing that I would like to say is most of this presentation is taken from the paper by Atiyah and this paper by Lowell Abrams. I'd also like to thank Michael Aswood for discussing a little bit about the physics side. Whatever I was able to discuss today about the physics side was because of the discussion with him and the discussion with Professor Khalkhali I had a couple of weeks ago. So thanks to both of you. That is going to be my presentation. And if you have any questions, please let me know. Thanks.
Okay, thank you, Baljit. Yeah, excellent timing and very nice presentation. Thank you.
Thank you very much.
Okay, any questions or comments? So in the case of this, when you have this Frobenius algebra is the group algebra of a finite group, as you mentioned. Just to remember, so what we attach to a circle then is just the group itself, or what? What vector space? Is it a group algebra?
So you're asking what the group algebra is. So no. Okay. So in this case, we just associate to the circle just the whole algebra, and to a union of n circles, we associate the same algebra tensored n times.
That's right. Yeah. But in the case of truncated polynomials, to the circle, we associate again, of course, the truncated polynomials, but yeah, so the difficult part is to decide what morphism should be, right? Yeah.
Yeah. Also, I think during our discussion, you asked me to work out the case for Rn. The issue with that is there needs to be, along with the pairing, which you gave as the dot product, there
Yeah,
also needs to be a commutative algebra structure, which is not possible
that's
on
right.
like an arbitrary
That's right.
Rn. So I couldn't work that out.
That's right. That won't work. But yeah, but any finite dimensional Hopf algebra would be good, right?
Yeah, actually, there are, I think these group algebras are examples of Hopf
These are,
algebras.
yeah, these are Hopf algebras. Yeah, exactly.
Yeah.
They are examples of. Okay. Well, excellent. So looks like there are no other questions.
Okay.
Okay. Thanks again, Baljit.
Uh,
So yeah,
Thank you very much. Thank you very much.
thank you. Okay, now it's I believe it's Jenny's time to share the document, her document.
Hi.
Yeah, so we can see it very well. Thank you. Yeah, great.
Okay.
Yeah, you can start, please. Yeah.
Yeah. How do I? God, I want to start the slides, but I forgot the the key to start.
Oh,
Uh,
just if you push on return won't work.
oh no, it's last time I just full screen.
Oh, yeah, full screen. Yeah, that's a good idea.
Okay, cool. So today I'm going to talk about the combinatorics of counting surfaces from Tat's recursion to topological recursion. This is based on Einer's textbook, chapter 1 and 2. So this is the outline. I'm going to talk about the introduction and the permutation model, topology, automorphism and symmetry factors, generating function, Tat's equations, matrix model and fat graphs, dual graphs, dual maps, loop equations, and the Virasoro constraints. So this is the bridge between polygons and geometry. So we have a central problem. We want to count weighted maps of genus G with K boundary components. We have three independent motivations. We have a random geometry. We map the model 2D quantum gravity, and we semi over maps with this weight e to the negative mu b mimics the gravitational path integral. And we have a matrix model. The Feynman expansion of a Hermitian matrix integral is indexed by maps via the 1 over n genus expansion. And algebraic geometry, the map counting generating functions relate to the intersection numbers of MGN. So we have a key idea. Combinatorics of polygon gluing is the topology of compact-oriented surfaces. And we can see that there's a timeline of major results. In 1962, Tat came up with planar map enumeration. Tat is a Canadian graph theorist. And in 2007, Einar the Orientin topological recursion. So you see that there's the hoofs, 1 over n expansion. There's the Bibbs theorem. There's the Witten conjecture. There's the Kontsevich matrix area integral. There's the Mirzakhani recursion. And so we have we see that there's three parallel worlds. We have maps surfaces, and the Beeps connects that with matrix integrals. And we have a spectral curves connected with matrix integrals. So our goal of this talk is to build the three bridges. So we'll see the definition. We label the map. is you see there's a finite set of darts. Darts are half edges, and we see cycles of theta corresponds to faces, and we have a fixed point-free involution such that the cycles of alpha are edges. So vertices are cycles of theta alpha. So you can see we listed an example that this is on a torus. So we have the reason why we know it's a torus is the genus is 1, and this V minus E plus F we can cover its Euler's formula and it counts the genus. So here you can see that the beta has the size 6, and we have a sigma is 1, 2, 3, 4, 5, 6, and alpha is 1, 4, 2, 5, 3, 6. So the way it's grouped, you see that the cycles of sigma alpha are vertices. So it's 1, 5, 3, 4, 2, 6. These are vertices. And then we just map it back to the definition, and you'll see that this is a concrete example, how we define the labeled map is a triple. So alternative definition is that a map is a graph such that it's cellularly embedded in a compact-oriented surface, such that every face is homeomorphic to an open disk. So this is the equivalent theorem, saying that the permutation model and the cellular embedding model are equivalent. We can do a proof sketch, like each cycle of the sigma defines a polygon with gluing edges via alpha produces a surface. So conversely, we can orient the edges to get the darts and read off sigma alpha. So we also can have rooted maps. We have a root is a marked dart. This routing will kill the automorphism. So the automorphism size is 1. So we also can show you the concrete example. We do a key check here to see that chi equals 2 minus 2g minus k. So the genus is 1. It's a torus. And you can see that it's the vertices minus the edges plus the face is 0 in this case. So that's the Euler characteristic. It's all integers. And the theorem classification of oriented surfaces is you using this chi, and this 2 minus 2g minus k. A sphere is 2, and the disk is 1. Torus we saw is 0. Annulus is 0. And the genus minus g is 2 minus 2g. So you see that we classify the oriented surfaces like this. This 2 is the Euler's number on a sphere, you can see. So we have edge counting. Let nj be the number of j-gon interior faces. Let li be the length of the ith boundary. So every edge borders exactly to face size. So you count the edge twice, so you have this equation. Sorry. You count the edge twice, so you have this equation. And the main identity from the chi is we substitute that back in, and we get this dividing by a half to get the edge. So special cases is that for triangulations, you can see that j is equal to 3. So we have 2E equals 3F plus the sum of all the length of the ith boundary. And for quadrangulations, J equals 4, you have 2V plus 2G minus 2 plus K equals the sum of all the length of the ith boundary. So these are two special cases you can substitute back into this main identity to see that this works. This comes from edge counting. So Tutt's formula is what he came up in 1963. Let Rn be the number of rooted planar maps with n edges. And this is a combinatorial formula he came up with. And this is approximately C times 12 n times n to the negative 5 half. And this is bijections in combinatorics. We can see that rooted quadrangulations are well labeled plane trees. And the general planar maps are mobiles. And the scaling limit is that the Brownian map as the metric space limit of large random planar maps. So we have a limit, like in the infinite case, how a large random planar map behaves. We define an automorphism of this tuple B sigma alpha as the bijection of phi going from B to B with phi sigma phi minus 1 equals to sigma, and the phi alpha phi minus 1 equals to alpha. So we have a theorem, the rooted maps have trivial symmetry. So if M is rooted, then automorphism is 1 we saw. And we have an orbit stabilizer formula. We see that we want to relabeling this group, but we preserve the phase structure. We'll permute the nj copies of j-gons and their rotations. This will give you the product expression like this. So the automorphism times the number of gluings is equal to this, the product. So the permuting the copies and the rotations, you will get this permuting formula. So from labeled to unlabeled, each labeled map contributes 1 over the size of the automorphism to the generating function. So the symmetry factor, exactly as in Feynman diagrams. So we'll see that in a loop, which is 1 vertex, 1 edge, then the weight is half. The automorphism is 2. In a generic triangulation, the automorphism is 1, the weight is 1. So this goes from labeled to unlabeled. Then genus G, K boundary generating function is the expression is like this. We are summing over connected maps of genus G with K labeled boundaries. So we go with the summations over all the boundaries. So the variables here are T is vertex weight, Tj is the weight for j-gon faces. So we're doing it over the faces. And then xi minus li minus 1 encodes the boundary length li. We also produce it, we do a product over the faces and then over the boundary lengths. So we define free energy. When K is equal to 0, F is equal to this expression, and the Fg is equal to W0G counts closed genus G maps. We're working with long natural log G equals F restricts to connected maps. So we have a residual extraction, the amplitude for boundaries of fixed lengths. We extract the residual. There's a minus 1 to the K factor we use that to calculate the amplitude. And then there's a genus expansion. We see that the planar is G equals 0. The terms dominate at a large T. So F equals T to the negative 2 F0 plus F1 plus T squared F2. So at a large T, the planar terms will dominate. So in a disk case, G equals 0, K equals 1, you see that W10X is the main object computed by the TAT equation. So this is the example we're giving. So the TAT, the residual extraction that you can see that if we use the genus equals 0, K equals 1 case, then the W10X, we extracted this value from the TAT equation. So pure quadrangulation specialization. We'll set T4 equals to GS because it's a quadrangulation, and all other TJ equals 0. Then the TAT equation becomes this characteristic equation. Then with a solution, we can solve. This is just the formula. So we branch cut on AB and we get the spectral curve, C. Y squared equals X minus A, X minus B. Then we have a WX is approximately 1 over X as X goes to infinity. This is a normalization. So we have a critical point is that as GS equals GSC branch points collide, the series diverges and signaling a phase transition continuum limit. So this is a Brownian map in the limiting case. So we have a strategy. We'll peel the root edge of a planar disk map. We will do a peeling. So for G equals 0, K equals 1, the boundary length L plus 1. So we get this expression. This is the recursion. We have two exhaustive cases. These two covered all the cases. We have a bridge. We root edge removal disconnects the disk into two smaller disks of length J and the L minus 1 minus J. And we have a face. Root edge borders are interior J-gon, reducing boundary length by J minus 2. So you either go down by 1 or you go down by 2. You go down by 1, that's a root edge removal that disconnects the disk into two smaller disks. You do a root edge if the borders are interior J-gon, then you reduce the boundary length by J minus 2. That's a face removal. So you have this recursion covering these two cases. So we have a general TAT recursion, and we're going to explain the contributions of these four terms. So the first term is we split the boundary L1 across genus H and G minus H. The second term, we merge the boundary L1 with LM. We're reducing K. The third is we decrease the genus by 1. We create a handle. The fourth is we have a root edge borders a J-gon. We peel the face. So these are four exhaustive cases that creates this TAT recursion. And we have a partition function, which M is an n by n Hermitian matrix. So then we have a Wick's theorem. We have a Gaussian propagator. All moments factor into pair contractions. So it computes the moments using a factor, using a product of pair contractions. And we have a power counting, a diagram with V, E, F, the vertices, edges, faces will give you, according to the Euler's characteristic, F minus E plus V will give you n to the chi. And that's a 1 over n expansion, genus expansion. So these are definitions, and Wick's theorem is a Gaussian propagator. We have a double line notation. Each propagator, we explain Wick's theorem, each propagator is a double line carrying indices I and j. A vertex is a cyclic meeting of strands from trace of m to the k. A closed index loop is a phase. A genus is determined by chi is equal to f minus e plus v. So 't Hooft in 1974 came up with a large n limit selects planar, which is chi equals 2 diagrams only. So there's a key duality that fat graphs are dual to maps. Like vertices are to faces, faces are to vertices, edges preserved. So this is fat graphs are duals to maps. We have this Bips 1978 theorem, which this theorem is the combinatorial map counting problem, and we've recast it as evaluating Gaussian integrals. So we have a planar case, leading order you can see is n to the 2. And the torus case, the leading order is n0 because G is 1. A higher genus will be suppressed by the n minus 2 per handle. And the large, because higher genus you have more handles. And the large n limit, we'll see it becomes a planar map. So this theorem is counting, and it map counting, and it encompasses higher genuses. So it is the sum of all the maps is computed in a product formula. Whereas we can take the log of Zn, and then we get we get a formula with its genuses and the faces. So we have a construction of the dual map. We're given a fat graph, place a dual vertex in each face, and connect the dual vertices across each edge, and preserve cyclic order. We have a duality correspondence. This fat graph is a dual graph. Vertices to faces, faces to vertices, the edges to edges, and the chi to chi. So now we have a loop equation. We let v prime equals to this expression, and we have word identities. So we'll see that this is exactly the Tata equation. We're confirming that the matrix model and the combinatorial approaches agree. So we have a planar case. You will see that we covered the planar case. We have this matches with the Tata equation, and this is the spectral curve. The W10 square is on the left side. So this is a Schrödinger-Dyson loop equation, which we've let the V prime equals to this. So this is the matrix approach. That is the combinatorial approach. And we have a Virasoro operators. This is involves derivatives, and there's a theorem. So for the string equation and the dilation equation, there are some identities. And then I wouldn't go into too much detail into this because it involves calculation. The theorem states that LK Zn equals 0 for all k is greater than -1. Ln is equal to m minus n, Lm plus n. So this is just the identities you can confirm by calculating. So this is the operator definition.
What is that n? Sorry.
Sorry.
Oh, is the partition function at level n? Okay, right.
Yeah. Yeah,
Okay, right.
yeah. So
Yeah.
we have a definition here. Acting on long Zn inserts a boundary of variable length. So this operator, when we acting on this long Zn, we insert a boundary of variable length. And we have another theorem where we acting at the multi-boundary. We have a repeated differentiation. That's the cumulants of the boundary operator. We can feed it directly into the anard orienting recursion. So if you repeatedly operate like we're using this operator, then on the long Zn, then you have a multi-boundary correlators. You can do a repeated differentiation. So this is a nice relationship. And then we have a spectral curve definition. The spectral curve came up before, and it's an algebraic curve, and such that y squared is equal to mx squared minus 4px, where yx is defined like this, and it's the planar resolvent. So in the quadrangulation model, y squared is x minus a times x minus b, and branch points is the endpoints of the eigenvalue supports. So because the way it's defined. And at the GS goes to GSC, C degenerates. The branch points collide. So that we can see the eigenvalue density. This is the eigenvalue density in this case. X is in AB, in the interval AB, and then PX is the rho X is the density, and then it can be because it's a spectral curve. We wanted to know the eigenvalue density so that we can solve for this equation. The setup is that we're given this four tuple with B, the Bergman kernel. We set omega n equals to WND, so repeated differentiation. And this is our final theorem, Einard-Ornstein, 2007. So this is a long equation, but what it says is the Z conjugate is the conjugate point. K, Z1 to Zn minus 1 is over all branch points. So it's a combines residual, combines the product, and this theorem is it uses a kernel to solve for the residual. So we the remaining topics are modular space, and the intersection numbers and Witten conjecture. So Witten conjecture is the generating function satisfies the KDV hierarchy. It's covered in chapter 3, not in chapter 2. And the intersection numbers is like we have this integral is non-zero when the sum of di is 3g minus 3 plus n. So you can see that if you put it in some small values, you can see what these intersection numbers are. So when n is equal to 0, g is equal to 0. When n is equal to 1, g is equal to 1. You can see what the intersection numbers are. And the moduli spaces and the we M M conjugate G and compacted modular spaces of genus G curves with N marked points. So these are extra topics. And we have a Kontsevich matrix integral. This is a Feynman diagrams are ribbon graphs cells proving the Witten conjecture. This is used to prove the Witten conjecture like a hierarchy. So KdV equation is this equation. We are not doing the combinatorial anymore. We're doing the matrix model. You can see that if I go back the hierarchy, so F satisfies so it uses an integral to with the trace to it proves this equation. And there are more applications. Gromov-Witten theory, which Calabi-Yau threefolds. I think you've heard of it. It's a remodeling conjecture, and not invariance. It's a topological recurgent spectral curve, and a random matrix universality, and the Mirzakhani recursion. So these are special cases of Einer-Ortin. The one we talked about. And the random matrix universality has to do a lot with eigenvalue. So where the largest eigenvalue is, remember we talk about eigenvalue density. So we talk about matrix analysis. The use a kernel to solve matrices. So there's remaining topics that are not covered in chapter 1 and 2, but could be explored. So what we covered today, we covered the maps, rooted, labeled, Euler characteristic, important, automorphism and symmetry factors, generating factors and free energy, generating functions and free energy, and the Tate equations, combinatorial, planar and higher genus, matrix models, fat graphs, Bibb's theorem. This is a matrix integral, and loop equations of Versaro constraints, spectral curve, Einer-Ortin recursion, Witten conjecture, and the KdV hierarchy. So we can see the dualities. Maps go to matrix integrals by Bibb's, and when it's large N, we talk about spectral curves, and then we talk about the intersection. So we have open frontiers, quantum curves, topological recursion beyond the algebraic geometry. So this is my talk. Thank you very much.
Thank you, Jenny. Yeah. Okay, excellent. So any questions or comments?
Oh, I guess I was wondering about the I think it was Pasteur's law, where the edges are at any value A and B. I wonder which matrix model gives those general edge points, where the branch cuts are between A and B in general. I think it was there.
Yeah. This question is for Jenny, right? Yeah.
Yeah. I think it was just yeah, the
Sorry,
one with
which slides were you referring to?
so the one with the branch cut, AB.
Okay, let me go to that slide. Oh, just a second. Well, AB, the branch cut. Here?
Oh no, at the end, it's Pasteur's law.
Did we have Pasteur's law?
Yeah,
You mean
because
Marchenko Pasteur?
Yeah, yeah. So I was wondering how it related to that. Yeah. So the with the branch cap. There we go.
Oh,
Oh, oh yeah. So that's the one.
so 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 sorry, what's your question? The
Um,
how it relates to?
yeah. So how it relates to the Marchenko-Pasteur law? I know it's derived from that eigenvalue density. Yeah, I guess from the definition of W1, um, it, uh, it could be recovered from a matrix model. I'm just wondering if that's um, these eigenvalues is there a matrix model they come from, or is it just from a differential equation, so eigenvalues in that sense, or
Uh, so eigenvalue density is like how the eigenvalue we can use to find them when the matrix dimension is large, then we have this in the complex plane, like there's a spectral curve. So in a random this is like in a random way, like that's why it's imaginary. It's complex. So this this is just showing that uh like how we can calculate them, like Wigner's law, like it's whether the eigenvalues are real or not, like we
Mhm.
I think it's it says the endpoints of eigenvalues supports. So I'm not sure what your question is, but I think it wants to know what the branch point collide, or they meet, or they separate.
um, yes, that one is interesting. I'm just wondering in general, because for all the matrix models we know of, the A is always minus B, um,
Mhm.
uh, and that's why I just wonder how we get general A and B. Um, the eigenvalue density comes just from integrating around the
Yeah. So
branch
yeah,
cut. Yeah.
yeah. I think, Brett. I mean, what you indeed in last few lectures we covered this quadriangular case. So what you do in that case, you use Weil's integration formula to reduce the integration over Rn, and then you use this uh, Laplace method.
Yeah.
We wrote down some equations for the equilibrium. So this is for finite n, and then as n goes to infinity, this discrete distribution converges to this continuous distribution that's denoted by, I believe, rho of x, or yeah, rho of x down there, right? And the those equations actually can be shown to lead to this spectral curve that's we have over there.
Oh,
And
that's right.
then you use this. So this is also a mixture of you use this still just transform to go into complex plane over the real line, and then this so-called Sokhotsky formula gives you rho of x back if you can compute W1 0. So
Oh, that's
yeah, so yeah, indeed, this comes from a matrix model. Yeah, you
oh,
see,
that's true.
yeah, we had BIPZ, which is asymptotic expansion, but it doesn't give you the form of the form of spectral density function. But this method does give you that, and this uh, Einard or end-to-end topological recursion is even more general, more refined information. Not only the density, but all the higher moments, or cumulants you can compute from that. Yeah,
That's true. Oh,
yeah.
perfect.
So
Yeah, I was just wondering if there was uh,
yeah,
a quicker way to find those spectral edges, but I guess it's just that usual
yeah,
ways.
yeah. In
But
fact,
sort
finding those spectral edges is tricky actually.
yeah.
They are quite tricky. I mean, in the last lecture, we computed that for one particular model, quartic model, and that's quite tricky. Yeah. I mean, there's an algebraic equation that they satisfy, but yeah, right.
That's true.
Yeah, maybe Jenny wants to say something more. I don't know, but
Oh no, I was just I also want to know algebraically, like the book didn't talk more about it, but I want to know algebraic geometry wise how this
yeah,
spectral curve works.
yeah. That's again another huge topic, right?
Yeah,
Yeah. Okay, so looks
That's
like
perfect.
there are no other questions.
thank you very much.
Yeah, let's thank Jenny again. Okay. Okay, so next, Adrian, are you next?
Yep, I'm up next.
Okay, excellent. So you can start. So we're
Oh,
starting 10 minutes late, but we are still okay. Yeah.
you guys can hear me okay, yeah?
Yeah, I can hear you.
Okay, perfect. Okay, so I'll admit I'm a little bit nervous to talk. They've been really, really impressive so far. Um, so today I'm going to tell you about Witten's conjecture and Kontovich's theorem, which we just kind of saw in Jenny's talk. Thank you, Jenny. Um, but
Oh,
I'll be honest. This I'm not going to touch Kontovich's theorem very much. I'm going to focus on the conjecture. I have my own prerogatives on trying to understand and formalize the math behind some of the very surprising and shocking conjectures Witten has. Um, and so this conjecture, well, let's get into it. Okay, so just to schedule what we're going to do, I'm going to do a quick recap. We've seen it in quite a few talks, the compactification of the moduli space of marked curves. Then we're going to formalize these psi classes that are the objects that Witten integrates. I'll do a few examples. Then I'll go into the KDV hierarchy a little bit. Then actually state what the conjecture is, and try to show you how it actually is used and why it was such a big deal to get it proven. And then, well, I will try to pay homage to Kontsevich at the end, but I will not go into the math there too deeply at all. But luckily, Jenny told us a little bit about it. Okay, so the compactification of the modular space. So this is the Lean-Mumford compactification. So what we're going to do is we're going to look at some correlation functions, and they are integrals over the compactified moduli space. Now, this space, it's not smooth. How are you going to integrate? We're going to go into cohomology to help us. And so you definitely need a compact space. Okay, so this is the object we're going to integrate over. And by integrate, I mean we're going to pair with the fundamental form. And so we really should have a compact space. And so when we compactify, we're going to add these points. And these points will be curves, nodal curves. So they're not completely smooth anymore, but they're going to be stable. So there's a condition to these points that are going to be added, which are on the so-called boundary. They have to be stable. And so I'll draw a little picture, one example, what it might look like. We've seen this before. So that's like a Riemann sphere and a genus 1 part, a node in between. And it can be stranger than this, but this will show the condition for genus 0. So if you have, well, some people call these parts of the curve twigs. So this is one twig, and the second twig is over here. In this first twig, which is a sphere, so genus 0, you need to have 3 special points. So that's marks or nodes. So your marks on the curve, you need to have at least, well, 2 of them here. Okay, so you have 1, 2, and then the node will be 3 points. And that's what you will require. That's what you'll find for these curves on the boundary where you have a genus 0 part. Now, if you have a genus 1 part, you're going to need to have 1 special point, and that can be the node there. Now, the reason why we're doing this, these will fix the automorphisms of these twigs, and it makes it finite. So you don't want to have a continuous spectrum of automorphisms. You want a finite spectrum. Well, I put this here just so you know formally what's going on. It's an orbifold. It's called a Deligne-Mumford stack. The regular moduli space uncompactified sits inside. It's Zariski dense, and that's its dimension. So that's the genus minus 3. This is the number of marked points. Okay. Now, what we're going to do is we're going to get these cohomology classes. They're going to be elements of the second cohomology. And well, we're going to define these cohomology classes as Chern classes of line bundles. And these line bundles are going to be linked to each of your marked points. So we have n marked points, and so you're going to get n many line bundles. But to define them, we need something of a total space. Okay, so and what's going to fit the bill is this larger moduli space. So it's again marked curves, same genus, but you add an extra, almost like artificial marked point. So n plus 1 marked points. So if you have p1 down to pn marked points, you're going to add an extra 1 at the beginning. So this is a extra marked. And well, when you do this, well, where is this mark? It's somewhere on the curve. And so this mark is going to trace out the points of the curve. In other words, this is like the total space. It's going to be not just a point in there represents a curve, but you also have every point on the curve itself. And so we're going to call this universal curve over the space with n marks. Now these sections, what we get, sigma I, or I in. So one of them for each of the marks are sections. And well, what they are is you pick a point in the compactified moduli space, and what you assign to it is, well, inside you'll just find a curve and you will find its ith marked point. So there are n of them, and you'll get n of these sections. So each point, each curve, you assign to it its ith marked point. Now, when you do that, at that point, you'll have a tangent space. And well, I'm being a bit loose here. At the smooth points, you'll have a tangent space. And well, the tangent space to a curve, so a tangent space to one of the curves. And then you can dualize that. So you'll get a cotangent space, and that's a real dimension 2, complex dimension 1. It's a cotangent line. That's the line bundle. In spirit, that's the line bundle. Now we have these boundary points. It's not completely smooth, and so you have to do this thing here, which is use the relative dualizing sheaf. But you should think of it as the cotangent lines, and they fit together smoothly as long as you're along those smooth points. Again, to formalize this, you need to use this relative dualizing sheaf, whatever that is. Okay, and then, well, when you have these line bundles and you have one for each marked point, you have the Chern classes, which are elements of the second cohomology with rational coefficients because this is an orbifold. And so these are the psi classes that Witten uses. So now I'm going to get into the notation that Witten has. Good time here. Right. This is Witten's notation, and this is a correlation function. So correlation functions, one example of it. These taus here, this is notation, it's bookkeeping. So I'll just explain what this is. Each of these taus represent a marked point. Well, it represents a psi class for one of the marked points. So this one represents the first psi class. This index here is not telling you which marked point it is. It's telling you which power you're raising the psi class to. The reason why we swap to this notation is because it doesn't matter which marked point you're using. They're essentially indistinguishable. It doesn't matter which one. And so this notation here just keeps track of, well, how many marks are you putting in to your correlation function, and to what power are you raising each of their Chern classes. So formally, this is what it is, and this integral means, well, you're pairing this form with the fundamental form. So you'll get a number if you plug in a top degree form. Okay, so this integral is non-zero. This is what I'm saying here. If you plug in a top degree form, so this is the dimension of the moduli. Now this here is notation that I'm going to be using moving forward. So this is a marked point that's being raised to the power 0. And this S0 here tells you how many copies of it came out. So you might have something like tau 0, and then let me put a few more, tau 1, tau 1, tau 1. In this notation, well, okay, this is obvious, but this is the notation that they're going to use. And so these are just indices. So this is a way to write down essentially every correlation function, and we're going to work with those. Now, well, we saw this just now, but I'm going to dig into it now. The string equation, integrating over this moduli space. It's easy to say the correlation function is just this integral or whatever, but they're hard. How do you actually do that? This is one of the tools that you have that will give you that recursive flair that I'm going to try to bring together at the end. And so it's the string equation. And so when you're computing one of these correlation functions, which have a tau 0 there, so that means tau 0, it's some psi class, some psi raised to the power 0. Okay, and then you have some other tau classes. They can be whatever they are. As long as it isn't this very basic one, which is equal to 1, actually. As long as it's not that one, you have this relation holding. And this relation says that you essentially get to clip off a tau 0, and you shift down the next one. And the others, well, they just remain there. So this is kind of cool. You get rid of a tau 0. This string equation does that for you. Now, this is just like a general property. If you want to see combinatorially what happens in genus 0, for example, you can use this string equation. It's just a bookkeeping proof on the indices. This will recursively give you what this correlation function is for genus 0. And it's, well, it's these factorial things. I'm going to show you this with an example. So let's compute this intersection number. And so we have 1, 2, 3, 4, 5. So that's 5 marks. And then we have, well, what's the dimension of this moduli space of genus 0 with 5 marks? Well, it's 3 times the genus minus 3 plus the number of marks. Okay, so 3g minus 3 plus n. And that's just equal to 2. And then you have to check, well, what's the degree of the integrand? Well, everything here, these guys, they're all raised to the power 0. So those psi classes, whichever ones they correspond to, are to the power 0. And this one is to the power 2. So the degree of the integrand is 2. And so, well, these two things match. And so let's see what the intersection number is going to be. It need not be 0. And so we're going to apply this string equation recursively. And so we're going to try to isolate a tau 0 and try to clip it off. And so that's what happens here. So you isolate a tau 0 and you clip it off using the string equation. And then the right-hand side of the string equation turns out to be this. So that this is the 2 minus 1 here is the j minus 1. And then when you simplify that, well, you have tau 1 and you have 3 of these tau zeros remaining. We'll just reorder this so that the tau 0 is out front. We flip it off again with the string equation. And then what you get, tau 0, tau 0, tau 0 equal to 1. Okay, so this is just to give you that vibe that, you know, recursion is in the air, and it's going to come up more. Okay, so this slide here is a bit of a break, because as soon as I'm done with this break, we're going to go right into the hard part. I'm going to tell you about the Kurtovic-de Vries equation. Now, I had two big problems when I first saw these KdV equations. Well, I just saw one of them, I don't know, five years ago or so in PDEs. And well, the first problem is, how do you solve this PDE? And then the second problem, when my professor said it, well, Kurtovic-de Vries, how do you spell that? So I'll tell you the story. In 1834, Russell hears about this phenomenon of solitons, and he tries to see it happen. And so he has these horses pulling a boat. There's a sudden jerk of the boat, a mound of water forms, and it just moves forward in the river. So there's a mound of water moving forward, translating forward. He calls it a wave of translation because this wave, it does not break, it does not disperse, it just moves forward. And so he's walking along the river, then he gets on a horse, he's on a horse along the river, goes on for more than a mile. He describes this as the happiest day of his life. Now, way long after, the KdV equations get formalized. This is the first one, which generates the full hierarchy. In the 1960s, this gets formalized into the KdV hierarchy. So I'm going to show you what that looks like in our case. But first, let me set it up. So I'm going back now to the cohomologies. What we're going to do is take all of the correlation functions. Here they are. And this S here, it's supposed to be a bold S. It's any index. So this here represents any possible correlation function. What you're going to multiply it by are these variables. So there are infinitely many variables. T0, T1, and keeps going. You divide by this multi-index. So S factorial equals whatever the first one is factorial multiplied by the second one factorial dot, dot, dot. It's going. And well, you make this giant formal power series where the coefficients are the correlation functions. Okay, now the string equation, you can rewrite it in this notation as the derivative of this total free energy F. And then well, you differentiate it, and you'll get this as your right-hand side. Let me just tell you some notation that I will be using. When you have this double angle here, that notation means that, so this is the definition of the notation. It means that you're going to differentiate with respect to that variable. And then all of those partial derivatives, and you apply that operator to the total free energy. That's just notation. That's what the double angle burst means. And in that notation, this is what the string equation looks like. I just put that here for fun. Okay. So this is the KdV hierarchy. So it's a PDE. It's scary. Yeah. So U is going to be the second derivative of this free energy. Okay, so it's just two derivatives with respect to that first variable T0. And well, in our notation for derivatives of the total energy, it has this nice notation. Okay, and the KdV hierarchy, so here it is. It says that the partial derivatives are this T0 derivative of some polynomial of T0 derivatives. So this is T0. Okay, so all of these dots mean you differentiate with respect to t0. And this Ri plus 1 here is polynomials defined recursively. So the first one is just u, and the I plus 1 is given by this formula here with a single derivative here, a triple derivative here. Well, there it is. It's a PDE. It corresponds to that KdV equation for for solitons and waves moving forward. Where does it come from? Why does it apply here? Well, I can't answer that fully, and Witten did not answer that fully. But what he did say was this. So this is the conjecture, and it's the theorem of Kontovich. The generating function of intersection numbers. So u, when you plug in your total free energy differentiated twice, it perfectly satisfies all of the differential equations of the KdV hierarchy. And Ri plus 1 has this very nice simple form. So this is weird. What Witten did way back then, he computed quite a few examples, and well, of course, it all worked. It's a theorem now, so it worked. But it was very shocking and very surprising. Why is this appearing in intersection numbers on a moduli space of marked curves? So let me try to break this down a bit. So these things here, they're all really straight from the KdV equation. So let me write that from KdV. So you assume the conjecture true. This is by the definition what u is. If you take its t0 derivative, it means you're just going to get tau 0 3 times because you had 2 of them before. You take an extra derivative. Now you have 3 of them. Okay, by definition, the Ri is just this. If you want to take a derivative of that, the tau 0 part goes up by 1 index. So that's why you have a square here. If you want to take a third derivative, which you have in that recursive formula, well, then you'll add 3 more tau 0s. This is just a definition of Ri plus 1. If you want to take its first derivative, sure, you'll just add a power of tau 0. So this is all straight from the KdV equations, if you believe it's satisfied. Now, when you take all of these and you put it into the recursive formula, so you're putting it into this formula that we just had, well, this is what you get. Okay, well, what I want you to look at here is you have a tau I and a tau 0 squared on the left-hand side. And on the right-hand side, you have, well, tau 0s, you have an I minus 1, you have an I minus 1, you have an I minus 1. Okay, so it's a relation that if you have a correlation function on the left with a tau 0 squared in there, you will be able to reduce the index of the tau I that's next to it. So this is one way to see it. Now, you have these double angles here. So that's the derivative notation. If you set your variable t to be 0, what that will do, it'll give you when you do those derivatives, it'll give you the constant terms. And the constant terms are precisely just the correlation function. So exactly the same things that you see here. You just get the correlation functions with those same taus in there. Okay, so you have the same tau I here, and you have the I minus 1s on this side. So that's really cool. If you wanted to compute this correlation function on the left, you have this perhaps simpler one on the right. And I rewrote the string equation from before. I rewrote it here. And so it turns out that these two together will let you determine any correlation function that you want. Okay, so what I want to say to convince you of that, it's not too hard to prove, but you have to do a little bit of work. If you had a correlation function with a tau 0 squared, you'll use this one. And you will reduce it to the right-hand side, which is a little bit easier. And if you had a correlation function that didn't have a tau 0, what you'd do is you'd go the string equation in reverse. So you would use this side to input a tau 0 to your formula, to your correlation function. And then, well, if you need 2 of them to get tau 0 squared, you would use the string equation twice, and then you'd be able to use the KdV equation. And it turns out, well, this will determine for you every correlation function. Uh, and that's really cool. Finding these correlation functions are not easy, are not known. Well, they are known now because of this method. And so this was very shocking. I told you that I was not going to get into the Kontsevich proof. He uses the matrix array function. Let me swap to my references for a second here. So this first one here, Witten's conjecture, and then the Kontsevich proof. And I'll say that this is a really good reference here if you want to get into this gently. I will try to sorry about that. Try to pay homage to Kontsevich now by telling you about an interview that his advisor, Zagir, of course, Harry Zagir, the same one, said about Kontsevich. So in 91, the Arbeitsagang, so it's a conference. Michael Atiyah gives the starting lecture. So in this conference, they always went last minute. What are they going to talk about is kind of decided on spot. And Atiyah at this time normally gave the first lecture. And in his lecture, of course, he was going through Witten's conjecture, why it's a surprising big deal. And then after Zagir tells him that, my student is going to be the one to prove this. He said that Kontsevich would prove it. And Zagir's own words was that Michael Atiyah looked at him as if he was incredibly stupid. Now, at the end of the conference, there's always this boat ride, 3 hours upstream, 2 hours downstream. And throughout that entire 5 hours, Atiyah sat with Kontsevich, who essentially defended his proof and convinced Atiyah. Within that weekend, it might have been proven. I'm not too sure about that statement, but within that weekend, Atiyah was convinced that Kontsevich had proven the Witten conjecture. So with that, I think I will end this talk. Thank you for your attention, and if you have any questions.
Thanks, Adrian. Okay. Are there any questions? Yeah, you cited paper 3 by Penner. So how does it enter into the game?
I'll be honest. I put my references down that I had printed, and the Penner one I did not actually touch. It was the original plan to look at Penner, and then when I found this last one here, it was just too good.
Yeah. No. That's fine. No, I mean, yeah, indeed, Penner gave a proof of Zagier's theorem, which I tried to prove in class. I left some details still because it takes really like 6 months to prove that theorem itself. But but after Harrer and Zagier, Penner gave this proof using matrix integrals. So I believe. Just a second, if you allow me. Yeah, sorry about that. Yeah, so and then he gave a proof using matrix integrals of Zagier's Harrer-Zagier. You see, they computed the orbifold Euler characteristic of these moduli spaces, right?
Right.
And in this Kontsevich-Witten business, they go deeper. They actually say something about cohomology of the. Of course, cohomology of modular space is not computed yet. Nobody knows what it is.
Yeah, that's still very much open. Yeah.
Yeah, that's very much open. Yeah, but first of all, one comment would be nice to see if this Harrer-Zagier theorem follows from Kontsevich-Witten theorem conjecture. Yeah. I guess it should be possible, but I haven't seen it. It may be well known, actually. And second is that perhaps Konsevich's method is inspired by this Penner thing. I think he refers to Penner's because he came up with a different cellular decomposition for the moduli space, which is more adapted to the problem than the one that Harrer-Zagier was using. And he mentions this in the paper, actually, Konsevich. So Okay, but anyhow, so this is something that drew my attention, that paper by Penner. Yeah. Yeah. Are there any other questions or comments? Brett,
I
you
guess
don't have?
I'll add one comment for the audience. If you don't have a PhD yet, Koncevich got his PhD in these 23 pages proving this conjecture. So maybe that's a good goal to aim for.
Yeah. Right.
Solved in one weekend. Thereabouts.
Yeah, nice. Yeah. Very good. Okay, so Brett, you don't have any questions?
No, I think that's pretty good.
Hmm.
Yeah, I always like the KDV hierarchy. It's definitely an open field.
Hmm.
It even relates to how uh, like if you mix hot and cold water, like these solitons and
Hmm.
uh, in the approach to thermalization, it's more complicated than you think. So it's kind of
Yeah,
fun stuff.
that's true. Yes, indeed. Yeah. Indeed. Yeah. My God. Yeah. That's quite interesting stuff. This integrable systems. Yeah. Okay, looks like there are no other questions, so let's thank Adrian again. And the next talk will be by Alex Abramovich, I believe, and it's at 4 p.m. So Alex needed some time to get to home and then give his talk. So we come back at 4. For those who can attend, I'll be here for sure. Yeah. Okay. Then have a good day. And by the way, make sure to send me your slides. And also, if you are consenting, your talk will be posted at Fields on Fields YouTube channel or not. So that's okay. So I'll just close the thing for now.
My presentation is on Chern-Simons theory in discretized algebraic topology.
Hmm.
So first of all, here's an overview of what I'm going to cover. I'll start off with discovering Chern-Simons theory with topics like, first of all, going an overview with gauge theory, covering the equations of motion of Chern-Simons and the pure Chern-Simons model. And then I'll go into action in terms of anion and behavior, Wilson loops and lines, and Wynn's approach. And then I'll shift from abelian Chern-Simons to non-abelian Chern-Simons, and I'll delve into knot theory for a little bit, and then show a cool TQFT application. So first of all, a gauge theory review. So why? So why do we use gauge theory is my question here. So a benefit of gauge theory is we don't want our Lagrangian to change under any local transformations from Lie groups. So we want to have a local invariance. This local invariance comes with minimal coupling. So as an example, I said, let's start with a Dirac field. So I have the Lagrangian defined here with the Dirac fields, and this has a global U1 symmetry. This global U1 symmetry implies a global invariance. So you can see here, I represented the global invariance with this AI alpha term, which is pretty conventional. And I also described symmetry with a locality operation, where alpha maps onto alpha x, which means any transformations in space, whether it be like rotations or translations, you should still have invariance. That's what we're looking for. So if we start off with, okay, I'm gonna actually start writing stuff. If we look at this term here, right, this first partial with respect to the Minkowski space, we can actually map this onto. So we can map this term onto. I can write a little bit better phi than that. Using the global invariance, we should get that E I alpha x. Oh, sorry, it's a little bit ugly. E I alpha x multiplied by the
I think
symmetric.
we cannot see what's being written.
Oh, you can see what's being written.
No.
Mm.
Oh, That's frustrating. Oh, there's an annotate tool actually on the top. I see an annotate tool. Let me try that. Let me go onto the annotate tool and see if that works. Can you guys see this? Like, that's Google.
Yes.
Yeah, okay, that's good then.
Now works. Yeah. Great. Yeah.
I'll change the color and see if I can change the size maybe. Yeah, I think I can change the size.
Mhm.
Awesome. So again, we're gonna do a mapping. So we start with our partial with respect to the Minkowski space over our potential. And this should be mapped onto using our global invariance, we're mapping this onto EI alpha, and we're taking this partial term, right? So we're basically just taking we're just using the product tool, right? So we're just taking the partial derivative with respect to the EI alpha phi term. So we should get EI alpha partial of mu plus AI partial mu alpha, and then we're also gonna multiply this by our potential, right? So what we can see is here, this second term actually has an equation of motion changing over space. So if you take a look at this second term, there's dependence on the metric, right? Which is problematic. So instead, we should introduce a gauge field, right? So we introduce a gauge field, the typical A mu gauge field. This gauge field is going to come with a covariant derivative. So we're going to map from partial mu onto d mu. And this is the description of the covariant derivative, so I don't want to write it out again. Therefore, by doing this operation, we can take the covariant derivative with respect to phi, right? The covariant derivative with respect to phi, and get that it should map onto EI alpha x with d mu phi. So this is almost exactly this. This is our global invariance, right? So we see if we introduce a covariant derivative, we actually get a global invariance. So here's an exceptional example of where gauge theory can come into play, right? By providing an invariance. So these interaction terms are going to be consistent with local gauge invariance, and they're not going to introduce any new parameters. Additionally, one reason why we use gauge theory is for connections and curvature. So if we have our one form gauge or one form A, our curvature can be written like this, right? So we have our differential term plus our wedge product. This term specifically is a gauge covariant where the connection A is gauge invariant. And the connection here, the third bullet point, on the G bundle over our orientable manifold is a skew Hermitian matrix of trace 0, 1 films, or sorry, trace 0, 1 films. And that's also going to come into play. Once we're going to be using our G bundles to start solving our Chern-Simons theory and our partition functions, that's when it's going to be very important. So I'm going to clear this for now. There we go. And I'm going to move on to the next slide. Like this. Okay. All right. So an introduction to Chern-Simons. So first of all, I made a little bit of joke in the beginning. I said just use Yang-Mills. Well, there's a reason we don't use the Yang-Mills, right? So if you have your standard representation of Yang-Mills, you know you're going to have. Oh, let me scroll. Your standard representation of Yang-Mills is something. Oh, hold on. I'm using the wrong pen tool. Yeah, it's frustrating that it doesn't let me use my pen tool because it's a little bit better. But you have your 1 over 4g squared, and immediately you see that we have a metric introduced, right? Before I even write the integral term, right? And that's problematic because we want global invariance, right? So instead, we're going to try something out called Chern-Simons. So first of all, I'm going to start out in 3-dimensional Minkowski space. I'm not even going to move it to 4-dimensional quite yet. So just so I can like present the example. So we're going to have 2 spatial and 1 temporal dimension. So as I showed here, R21. And our Chern-Simons 3 form is written like this. So here's the general description for the Chern-Simons form, and I'm going to break down what different parts of the equation mean. Firstly, this k term is our Chern-Simons level, and it's a real number. It's an integer in quantum mechanics. We'll get to that in a second as well. And when you get to quantization as well, that's when it's really important that it's an integer. But it's really similar to Yang-Mills theory in that it has a strength level, right? So it just measures the strength of the theory. And in terms of algebraic topology, it measures the wanding of the gauge field. It measures the level of wanding. You can see here under large gauge transformations, it must be quantized. So this the Chern-Simons action is mapping onto itself plus this 2 pi k n term. And that shows some gauge invariance. And this is called our topological quantization condition. For the next term inside of the equation, we also have the Levis-Civita symbol. I'm assuming everybody here saw that, but I wrote in a kind of a condensed form where it's just -1 to the n, where n is the number of permutations in x, y, z. Again, we're working in 3 dimensions here. So in 4, the tilde would be replaced by another variable. But you might also see in the form where it's like odd, -1, and then for even permutations, it's +1. And then finally, we have a gauge field A mu for U1. So we're working in U1 for the time being. Also here, I actually finished, in my notes, I finished the integral for our Yang-Mills action, just so I can show some things that might pop up as well with that. So I have that. First of all, there's our Hodge star. Our Hodge star basically represents a correspondence between our n basic k forms and R of n. So it's basically written, you can see it as, you would see it as like dx of 1, and then ... and then dx of n, where these are all wedge products with each other. So it'd be dx1, dx all the way up to dx of n, which are all wedge products. And then for an example, the Hodge star of 1 would be represented by wedge products between dx, dy, dz, assuming we're in a 4-dimensional space, right? Or sorry, a 3-dimensional space. So this is an R3, right? So this is also going to pop up when we look at Chern-Simons theory and its respective Hodge star. But let me clear this out, and then I can move on to the next slide. There we go. Yeah, there we go. Okay, so our 3-form classical equations of motion, right? So I want to show now the equations of motion for our Chern-Simons theory. So first of all, we're going to do the pretty standard thing of assuming no variance in the Chern-Simons action. It's also going to impose a flat curvature, right? So we have f equals 0, where f can be written also as dA, as the differential form. And what I'm going to prove here is that the variance in the Chern-Simons action can be written like this. So firstly, I'm going to introduce a nice scroll. I'm going to introduce a gauge potential A mu, or a gauge field A mu, and I'm going to map it onto itself plus some variance in A mu. Therefore, our variance in CS using the previous equation, so using the using this equation, I got that the variance in CS should be written like this. So this, I just took a product rule here basically. The first term is fine, but we need to do integration by parts on the second term. So with some integration by parts, you can rewrite this integral as this, right? Where the UV term, right, the non-integral term is the boundary of the manifold we're integrating over. But now there's kind of a problem because we're defining our gauge field with respect to a different index than we are our first term, right? So what we're going to do is we're going to do a swap. We're going to do a variable reassignment between rho and mu. This also implies a swap between the gauge fields rho and mu, and a swap between the Levis-Civitas indexing in rho and mu. But the thing is, that's actually pretty easy to solve. All we need to do is one permutation, and then now we have the same Levis-Civita, but it's just negated, right? Because it's an odd permutation. Therefore, our Chern-Simons can be rewritten in this form after we perform the integration by parts and combined both terms together. By utilizing the differential form of the curvature, along with the anasymmetry condition, we can basically take the curvature here, apply both derivatives, and then apply the anasymmetry condition on f of new rho, and then we can derive that the variance in CS should be written like this. And then after you perform the integral, you're going to get what's written above. So this is a pretty simple example, right? We're working 3 dimensions, in fact, flat spacetime, and it's abelian. But this is kind of the approach we're going to take, just more expanded upon in different spaces for Chern-Simons. Now I'm going to move on to the EM example. So I have 2 images here. And basically what Chern-Simons theory does, right, is we have our Maxwell's theory, right? But Maxwell's theory obviously has these variances, right? It doesn't have a global invariance, right? So we need to introduce a Chern-Simons action term to account for the for what Maxwell's equations doesn't hold up to. But the first thing we're going to do is we're going to write Maxwell's equations in terms of gauge potentials. So you can see here I rewrote Maxwell's equations in terms of gauge potentials. I also am introducing a matter current. So there's going to be a associated matter current, J mu and then there's going to be the density, the charge density, and there's going to be the vector that represents the matter current. And by introducing this matter current, we can actually solve these equations the same way we solved the 3-form equation of motion in the previous slide. I didn't write that out, but you can just apply it the same way. It's the same exact procedure, and you actually get these 2 equations here, which describe some pretty interesting results. For one, you can see that our charge density here is represented by an integer multiple of our magnetic field. So what you get is you basically get these stationary charges in predicted by Chern-Simons action as having these magnetic flux tubes. I do want to say that there aren't magnetic monopoles here because each of these charges would be created by pairs out of a vacuum, right? So each of the flux tubes would basically like cancel each other out. So there wouldn't be any magnetic monopole here. So that's just something to keep note of. But it basically shows how Chern-Simons theory can create these pretty interesting results that Maxwell's theory restricts, right? And then a similar thing for the electromagnetic field. We have the electromagnetic field related to a matter current proportionally, which means that you actually need to have some variation in the charge density, aka some like velocity or movement space time to create electric field. So you kind of have like a flip in what you'd expect in Maxwell's theory versus what you do in Chern-Simons. And then also in this diagram here, I represented an anion. I'm going to be referring back to this because it's really essential to how Chern-Simons theory behaves and what makes it exceptional. But for a background, an anion is just a 2 + 1d quasiparticle, and it has both these fermion and bosonic capabilities. So not only does it interact with other particles, but it also has its own particle matter. It also has its own matter current. So it makes it pretty interesting. So that's something else I'll be investigating. Yeah, I think that's all I wanted to talk about here. Oh, I also wanted to say that this relationship at the bottom is similar to what you'd expect out of the quantum Hall effect. So these have like the same exact predictions. Yeah. There we go. So now to go into some pure Chern-Simons theory. So now I want to move out of 3 dimensions and we're going to go into our typical 4-dimensional Minkowski spacetime. Formally, I'm going to define M to be an oriented Riemannian manifold, a 4 manifold. So it's going to be in 3 + 1D. We're also going to assume the definition is okay if E, which is a bundle of all connected, simple, connected compact Lie groups, is trivial. So we're going to make that assumption here. And A is also, again, going to be our Lie algebra valued 1 form, so our gauge field. And dA as our exterior derivative.
So
If you can see,
little a is capital A, I guess, right?
Yeah, I used A as capital A here, yeah.
Yeah, sure, yeah. No
Yeah.
problem. Cool, for sure.
I also took the trace function here and put it in. Oh, sorry. No, that's not what I did. The trace function here behaves like a line matrix trace on an invariant quadratic, and that's actually really important because we're going to use a property in a couple of slides to show how these invariant quadratics can solve an integral that's going to be useful for a partition function. So that's going to be relevant to the trace function in the future. But this is why I wanted it in this form. And then these two equations, so you can see this one on the top and this one on the bottom, they're the same exact thing, except I just the bottom one just uses f as the curvature. So it's a pretty simple derivation. You just substitute a plus a wedge a, or sorry, dA plus a wedge a for f, and you would get the same thing as above. Oh, so let me clear this at the bottom.
So what was B again? I missed the definition of B.
Oh, sorry, E. So E is the bundle. E is the bundle of all connected, simply connected compact Lie groups.
Right, but you are integrating over B, manifold B.
Oh, B. I know what you're saying. Yeah. So I didn't get to that yet. Yeah. So B is the boundary of B is the manifold. So
Oh, okay, right.
yeah.
Right.
So B is our 4 manifold, and then M is our 3 manifold.
Right.
Yeah.
Excellent. Yeah, very good. Yeah.
Sorry.
No problem. That's great. Yeah.
Let me. Oh, and then to go into the Euclidean partition function part. So now that we built some better intuition for what CS theory has to offer, we can introduce our partition function in this form. And our goal is to solve this partition. So the first thing we can see is we can introduce CSE, which is our gauge field configuration that is weighted by our action. So now we're weighting our gauge field configuration by our action. It's different from the standard action CS. This one has E in the index, and it's a different thing. But they're actually related in that. Let me go. In that the Chern-Simons action can map onto the weighted Chern-Simons via a Wick rotation. So we have a Wick rotation negative I CS here. So what we can do is we can actually apply this Wick transformation while keeping in mind that the partition function is going to be gauge invariant under large transformations, because that gives us the result that the variance in the Chern-Simons action should be supplemented by 2 pi k, right? And you can see this is the exact same quantization condition we had a couple slides ago, right? We had the 2 pi, it was 2 pi ik, but we had the same quantization condition. So what we can do is we can put this inside of the exponent for this integral, and we get that our partition should be the manifold integral m dA e to the I CS plus 2 pi k. I should write that a little bit better because it's a little bit messy. Plus 2 pi k. And again, all I did was I put these pieces of information into the exponent of E in this integral using the Wick rotation. And we get that this is equivalent to this above. So this is equivalent to this right here, right? So what we basically showed is we showed that the partition function is equivalent to itself multiplied by this e to the 2 pi ik factor. And the only way that can be possible, right, is if we have gauge invariance, right? So we showed that the partition function here under Chern-Simons must have gauge invariance. Now moving into the anion model and generalized action. So as I referred to before, our full action is going to be now defined as our Chern-Simons action plus our Maxwell action, right? Where the Chern-Simons action is basically acting like a fixing term, right? To fix to basically add invariance to Maxwell's equations. And what we can do with this is we can generalize electromagnetic U1 theory from 3 plus 1D into 2 plus 1D. And this is where the anion model is going to come back into play. our action is going to be defined now by this term, but our curvature on M now is going to be the EM field strength, right? So using our definition for Chern-Simons action, along with the definition for the Maxwell action, right? So this is what I introduced before, and here's the description of Maxwell's action. We should get the same equations of motion, and that's consistent. So you get these same consistent equations of motion. So what I want to do now is I want to compare Yang-Mills to Chern-Simons to see how do those equations of motions differ, right, on macroscopic scales. So since our lead gauge group is since our lead gauge group of G on the simple unitary of N has the same gauge fields condition. Actually, let me just go back to the other slide so I don't have to write it back out. Since it has this gauge field condition, the same formalization, what we get is a killing form right here in Chern-Simons of 1/2 and then the Kronecker of AB, right? And this is super similar to what we have for Yang-Mills. We have if you take the trace of these generators of the Lie group of G, so T are the generators of the Lie group of G, you get the same vector, right? And this is pretty interesting because it shows a relationship, a similarity between Chern-Simons and Yang-Mills, right? Additionally, if you look at both of their curvatures, they're pretty similar, except that Yang-Mills induces a metric, right? But if we're already assuming that invariance isn't a problem, if we're not like talking about transformations, they're actually the exact same, right? So we should expect that there's going to be some similar behaviors between Chern-Simons and Yang-Mills. So we can basically make like an ansatz, we can basically make a guess that what if we describe the action in terms of the sum of our Chern-Simons action and a Yang-Mills action, and just see what happens, right? So this is why I pointed to this action right here, because this is what's exciting, right? We want to see what does this look like, right? And this is kind of a little bit above what I'm doing now, but it's Chern-Simons Yang-Mills theory, and is basically trying to describe both local macroscopic and microscopic invariance with the Chern-Simons and Yang-Mills equations. I'm going to move now into Wilson loops and lines. Actually, no, there's one more thing I wanted to talk about. Yeah, there's one more thing I wanted to talk about on this slide. I also wanted to talk about the parity conditions. Both Chern-Simons and Yang-Mills violate temporal and parity conditions. So if you have some sort of, let's say, some map T that maps your time onto negative T, your Chern-Simons breaks down, right? You don't have the same predictions. And this is really important because it really restricts what we can do in terms of, we're going to get into it soon, our algebraic topologies, but there's a lot of focus into the orientability of manifolds, and if they're not oriented correctly, or we're not describing the manifolds with the right directionality, then you're going to get completely different results, and that's problematic too. There we go. So now going into Wilson loops and lines. So I'm just going to read out the statement here. So we must classify our gauge invariant observables without choice of a metric in order to preserve covariance, right? Since Chern-Simons theory alone has no local degrees of freedom. And to unpack what that means is, in order to preserve covariance, we need to compare our path ordered exponentials. So we basically have these exponential terms that describe our observables, and our goal is to basically solve for these observables in a classification system of partitions, right? So what we do is we introduce these Wilson lines, right? Wilson loops and Wilson lines. Wilson loops and Wilson lines are similar, except a Wilson loop is just a closed Wilson line. So if I ever say Wilson loop instead of Wilson line, it's just the same exact thing, but there's just a circle on the integral. But it's described by this equation here, and it obeys a gauge invariance under this transformation. In this gauge invariance, you can see this term here is our adjoint action, and this rotates our matrix value field. And this is important because it tells us if our transformation can be reduced to something that's contractible. And if it's contractible or not, it tells us how challenging it is basically to solve for the action on the topology, right? So what I'm about to show you is on a cylinder, it's pretty easy to get contractibility, but on a torus and by extensibility on like some sort of more complex manifold, it's not, right? Additionally, I want to introduce a definition that a transformation. Okay, actually, no. First, I want to say a transformation can be reduced. So if we reduce this adjoint notion into a transformation with a metric, we might get something like this. Also, so this is important to note because you can see how it's dependent on this partial term with respect to alpha, and this actually gives information about its contractibility, right? So if its mapping and the metric is not changing, right, but we have a partial term that's like, let's say alternating with respect to rotation, right? Then there's some sort of adjoint term, right? And then we don't have the kind Gaussian variance that we want, right? And then additionally, a Wilson loop is trivial. It's defined as trivial if the Wilson loop over a curve or the Wilson line over a curve is equal to 1. So if we take the Wilson line over a curve, we're going to see that in a second. If that equals 1, then it's trivial. Going into world lines in M. So again, our goal is to solve our quantum field theory by evaluating topological invariance. So using our expectation value for observables, like so, we get we get this condition where we need to observe these proper observables, right, in order to solve the partition function. So in order to do so, first of all, we have to make sure that the world lines inside of, I'm doing it for cylinder first, but in general, we need to make sure that our world lines are far away enough from the boundary so that they don't inflict a field on the boundary, right? Because then our partition function is going to be off, right? So we want them to be far enough away from our boundary. In this example, we're going to assume that they are, right? So I'm going to go into the cylinder example now. First of all, to describe what's going on, we have particle-antiparticle pairs being created here. I only showed 2 of them, 2 particle-antiparticle pairs, so 1 and 3 and 2 and 4 respectively. They're being created out of a vacuum Z0, which is like, you can think about it like it's a disk, right? This disk is in R2, but the world lines are going to be traced by time. You can see the time is represented vertically here from negative to positive infinity. So basically what we're going to do is we're going to trace these Wilson loops, right, over the world lines of the particles. And what we can see is if we use these Wilson loops as our observables, we can actually solve these partition functions, and it's pretty neat. So what we do is we induce a holonomy. Let's write it here. Oh wait, no, this is the wrong pen again. Awesome. If we introduce a holonomy HC with P being our path orderly operator. So we have P exp of IQ then we have our gauge here, and then dx mu. This is going to be the holonomy that we're going to introduce. And we're going to introduce it on our manifold. This manifold we can describe as Z cross Cartesian product between Z and the real numbers, right? Z being the spatial dimensions and R being time. Right. So moving on now to the next slide, where we're going to actually go into why this is relevant. We can now solve our abelian expectation values. So first of all, our abelian CS gauge group is going to give us these Wilson loops written like this, right? So we took the description of Wilson loops from 2 slides ago, right? And we put them in path integral form, right? We put them in the path integral form. That's pretty similar to what we want for partitions, right? Such that we have the same description. Oh, sorry.
How much more time you need? Because it's already, you start at 4, right?
Yeah. I'm halfway done, I think. I'm not, I'm a little over halfway.
Oh, okay. So because it's 30 minutes, like for everyone, but it's 5 minutes over time. I mean, you can take 5 more minutes and maybe focus on the
Yeah.
discretized part, if that's okay with you.
Yeah, I'll do that. Yeah. Okay,
Sure,
well,
sure.
I'll just go over this I'll just quickly
Okay, yeah,
describe
sure. Yeah, yeah,
it.
just yeah,
Hmm.
for sure, yeah. No.
So I solved these expectation values. I did there's some substitution here, but one of the things I referenced before, remember the quadratic functional integrals? Remember when I was talking about that? They obey the use of this inverse Chern-Simons. So you can see this inverse Chern-Simons relationship. And it's pretty interesting because if you use a green function on this inverse, you get a Biot-Savart kernel, which I thought was pretty neat. And this term right here, this JK -1J term, it becomes a double line integral over Ci and Cj, which I basically index paths. So instead of using A and B as paths like I did on the previous slide, I use Ci and Cj. And that's how I was basically able to solve these partition functions here for that example. So here's a torus, and Wilson loops can parameterize this phase space, but in spaces like R3 and S3, all these Wilson loops are going to be trivial, right? This is because they're simply connected. But it turns out in the manifold T2R, right? So our torus in the three-dimensional torus, our fundamental group maps to Z plus Z, right? So we actually get this classical phase space, which is the torus itself. So our phase space is U1 cross U1, which is super cool because we basically took a simple manifold with a non-trivial topology and we introduced particle behavior on it, right? And this is just like another step up from the cylinder example. This is Witten's method. I can just cover this briefly because I don't have a lot of time, but it's basically you take. I was going to draw an image here, but I guess I can do it real quick. But you basically take a manifold, and I use. Oh no, I actually did history one this time. You take a manifold and you introduce a cut on the manifold, and if you cut the manifold, you can actually evaluate the expectation values independently on the manifold using observables as Wilson loops. So you basically make the set of observables. So it's like WC1 R1 all the way up to WCN Rn, where R is representations on G, and it makes it a lot easier because you can basically break down these manifolds as representations of the gauge group, and you can solve these partition functions. And this is what Edward Wynne was doing when he initially published his paper on Chern-Simons theory. Let me clear this out. I was gonna do a quick cover of knots. Do you think it's necessary or a quick review?
I think it's okay. We can just move on. Yeah,
Oh yeah, that's what I was thinking. Yeah.
right.
But one thing I want to note is something that's less common to see is a Hopf link. So you have your not defined like this, a Hopf link, and then there's also a linking structure that I'm gonna go into. But I can talk about all that stuff on the next slide as well. That's okay. So this is the Jones polynomial. And basically what Jones polynomial does, it allows us to evaluate the expectation value of non-abelian Wilson loops on an orientable link L. So what you do is you basically introduce this Laurent polynomial specifically at Q at 1/2, right? And this is basically some background in Kaufman bracket notation. I'm not gonna go over that because I don't have a lot of time. But you can basically take some sort of knotting structure. So let's say I want to take the structure, as I said before, of the Hopf link, right? So I can take a Hopf link right here, and I can decompose this as polynomials, right? So I can decompose this as polynomials using this notation where y is in scheme notation, y is smoothly connected. Or sorry, no, y is negatively connected, and then z is smoothly connected. So you can actually deconstruct this Hopf link as A and then 0, 0 plus A negative 1 of this once twisted unknot. So this unknot that has one link, right? And then I'm not going to go through all the calculations, but this eventually turns into negative A3, negative A2, negative A1. And you just use the rules of Kauffman brackets here. But it basically allows us to dissect knots in terms of polynomials. And that's really important for what I'm going to do. And this is basically the context where it comes into play on knotting. And this is like the last like slide, and the rest is like references in the summary. So a knotting is so I'll spend my full time on this slide, I think. Is that okay? It's gonna take me like 2 or 3 more minutes. Is that fine?
Yeah, that's okay.
So unknotting is an extension of Witten's procedure. So we're gonna present an SU2 theory, right? Of Chern-Simons, so we can evaluate our partition function on Z of L, where L is our link, within our 3 manifold. So what we're going to do is, you can see on the graph here, and I'm actually glad that I didn't draw this one out because it would have taken way too long. You can notice, first of all, that ML and MR have the same boundary. And since they have the same boundary, we can write them having their equivalent boundary condition. So they have this boundary condition on this 2-sphere, right? We can just use sigma for their boundary specifically. They have their boundary on the 2-sphere. And we already quantized that. Remember, previously we quantized that on our toroidal, not toroidal topology, on our, hold on, let's click back to it. Yeah, on our toroidal topology, this is when we talked about a boundary, right? So knowing that this is the case, all we need to do is associate a physical Hilbert space, HL and HR, with the S boundaries. So what we do is we employ Feynman path integrals, right, to produce these two waves within our Hilbert space. So we have, sorry, 2 functionals within Hilbert space. So you have ML. Sorry, should be a ket, which is an element of the Hilbert space of L. Then we also have this R, which is going to be an element of the Hilbert space in R. So what we do is, now that we have our Hilbert spaces, we can introduce our partition function Z of L. Oh, sorry, I did not mean to clear that out. What is it? HR. We can introduce our partition function Z of L as ZML, or ZML, sorry, PhiML, while considering this UF, which is going to be our topology, with MR. And now that we have our partition function, and that we know that our Hilbert space in R is 2D, any 3 vectors must be linearly independent. So what we can do is we can deconstruct this as a linearly independent sequence, such that, say we have some like alpha ZL, where alpha is just a complex valued number, plus beta of ZL prime, again, complex valued number, and then plus gamma of ZL double prime, and then the primes just choose which manifold we're talking about. So if we're talking about M prime, then that's the linking number that's referring to. So using the linear dependence, we have this should equal 0, right? So substituting the quantization condition, the charge quantization condition, Q equals exp of 2 pi I over n plus k. So if we have this quantization condition to exp of 2 pi I over n plus k, where n is going to be the level of our simple ordinary group, or sorry, simple unitary group. So it's SUNK. Our Skene relation, which I defined beforehand, is precisely the same as our Jones polynomial, right? So basically what we're showing here is that we're suggesting that the interpretation of the partition functions for ZML of this SUN group in Chern-Simons theory is basically the same as the Jones polynomial. And remember, this is non-abelian, right? So we're basically showing that even in a non-abelian form, we can still get the Jones polynomial using this unknotting procedure. And yeah, that's the pretty cool thing. And then some further stuff I was talking about. Here are like some further like advances that we're trying to do right now in Chern-Simons theory, which includes increasing the precision of the functional integral, defining dA as a more rigorous measure on the space of connections is a big thing that comes in hand with this. Also figuring out, does CS theory produce a complete knot invariant? Since currently known invariants from Chern-Simons cannot distinguish all knots. Additionally, non-abelian quantization, as I showed, was pretty tough. Like that was still a relatively simple example. So working with how do you work with more challenging non-abelian spaces? That's another thing scientists are currently working on. And there's also something I read about a possible relationship to quantum gravity, which is probably the more like large scope type of thing. Where how are we going to relate this to general relativity, and how do we have a more firm relationship between Chern-Simons and Yang-Mills?
Okay, very good. Yeah.
And then here are my references. The top paper was the one that I chose, and yeah, that's it. Thank you.
Okay. Well, thanks very much, Alex. Yeah.
Yeah, thank you. I appreciate it. Do you have any questions or?
Thank you. Yeah. Are there questions?
Should I call on people?
No, usually I
You
think
just call out, I guess.
uh,
Oh, I think one of them was early on with the flux quantization. It was interesting because with Maxwell's equations, it's usually df equals 0,
Right.
but then this one, I guess, with the Chern-Simons theory in the abelian case, it gives the dual form of Maxwell's equations
Right. Yeah.
where it's interesting. And I was wondering how in the non-abelian case the magnetic monopoles would appear. I guess that's because with the flux tubes, there's the extra
Well,
space that can allow for the flux strings and that.
they're not magnetic monopoles because they're being produced in particle and particle pairs. The flux tubes are going to be, I guess it probably wasn't the best visual because the flux tubes would actually be oppositely oriented. Assuming like the four were two particle into particle pairs, they would be oppositely oriented. So there wouldn't. This isn't like saying that there's going to be a magnetic monopole, but it is saying that we can produce magnetic fields from stationary charges under global gauge transformations, right? So that's like the
Yeah.
right? And then relating that to what you said, in the non-abelian case, I think the same thing would hold, right? You would still have your Jones polynomial eventually, and then you would probably get similar results, right?
Oh, cool. Thanks.
Yeah, sure.
okay. Yeah, okay. Well, looks like there are no other questions. You in the title you mentioned discretized algebraic topology. What was that?
Well, the discretized element was basically the winding and the quantization type. I
Oh,
didn't
okay, right.
yeah, so this was also an
Uh,
element of discretized algebraic topology. I probably should have just said algebraic topology because I spent a lot of time talking about knots and non-invariants. But yeah,
mm.
that's what I
Yeah,
meant.
I thought you were going to do kind of maybe Chern-Simon theory over graphs and
Uh,
these sort of discrete structures, which is feasible, I guess, but with all this, but yeah, but that's okay, very good. So yeah, it was very nice, Alex. Thank you. I
thank
think
you.
now the course is over. Our presentations are over. There is one or two which they had some yeah legitimate reasons to delay their talks. I think they'll be in May. But well, I mean, when it times come, I will announce it. But I think basically we are done now.
Yeah,
So yeah, thank you so much for all of you being in the course and for all your presentations. It was really enjoyable. Yeah.